In the name of Almighty Allah, who is the King of Kings, the Lord of Lords, and the Master of Masters, this is Muhammad Aziz Khan. Today I'll be presenting my final year project with the title Efficient Real-Time Controller Design for Electric Drive Applications using HIL. Let me introduce my project partner, Engineer Atiq Kakar. This project was supervised by Engineer Jahangir Badar Sundar. Let's move toward the outline. First, I will be giving a brief introduction of our project, how things are integrated, how HIL Lab works. Then the problem statement will be discussed, literature review, aims and objectives of the project will be discussed, project hierarchy, how the project goes throughout the year, and the results and discussion, conclusion, and references will be discussed. Now move toward the introduction. What is offline simulation? Offline simulation works at a time step of microseconds and is a method of running simulations or experiments in a disconnected or isolated environment, separate from real-time data. It has limited accuracy and fidelity of the simulation model. Moreover, unforeseen events that occur in live systems may not be accurately captured in the offline simulations. This was the limitation of offline simulation as well. Now, what is real-time simulation? A real-time simulation provides controlled and isolated environment for analysis and experimentation. Real-time simulation focuses on replicating real-world dynamics and interaction in sync with real-time events. And how we can compare the real-time simulation versus physical setup. So here is an example which has been taken from a motor current, and it was given in a research paper. And the real-time simulation of the physical setup at different frequencies can be observed that they are nearly closer to each other, representing the real-world solution. And why hardware in the loop? So hardware in the loop, as compared to the offline simulation, real-time simulation results are more deterministic and very closer to experimental results. Offline simulation did not represent a real power converter behavior and cause unrealistic and incorrect results. FPGA, that is used in hardware in the loop, offers flexibility of softwares since no physical change is required in device and speed of hardware, thus offering time step at the level of nanoseconds. And hardware in the loop is used where a virtual plant is connected to a physical controller, which can be executed on a real-time simulator instead of a physical plant. This technology allows for more repeatable results and provides for testing conditions that are unable on real hardware, such as extreme events testing. Designs of motor drive controller, airbag system of a new car, cruise control system of a car, and integration of spaced robots are the few examples of real-time simulation technology. Now, how things are integrated in hardware in the loop. We require a workstation, a real-time simulator, a power amplifier, the actual system, and feedback sensors. Our workstation can be our PC. The real-time simulator is responsible for simulating the programs. It uses different softwares. Especially we use MATLAB, Simulink, or LabVIEW. And then the output is amplified in order to match the real system requirements, especially the devices under tests. And then the sensors are used to feed the responses back to the real-time simulator. Then what is inside a real-time simulator? It is a Myrio. Myrio and Sirio are responsible for data input and output, providing input and output peripherals. And this is NIPXI, PXIE that is responsible for simulating the programs. Now let's move toward the problem statement. Basically, the design of a real-time controller is a complex task because it needs balanced performance, safety, and cost. Time consuming, it is very time consuming and expensive physical prototyping is required. Moreover, the complexity of electric drive systems demand more advanced controller designs that can handle real-time operations. Now let's move toward the literature review. We did a lot of literature review, and here are some mentioned literature papers. Research papers of Jahangir Badr and Daniel Miracle helped us a lot in implementing HIL setup. The efficient hardware in the loop and digital controller technique for power electronic teaching, written by engineer Jahangir Badr Sumro. In this paper, he has implemented his setup for power electronics teaching. Here we got insight of HIL setup. Then comes efficient real-time controller design for test bench for power converter applications, written by Jahangir Badr Somro. It again helped us in implementing HIL setup, especially for efficient converter design, because we were also working on converters. Then comes the permanent magnetic synchronous motor control techniques. It was a kind of comparison between different control strategies with advantages and disadvantages, and we took a lot of help from this paper. Comes the aims and objectives of the project. Our aim was to apply our technical knowledge to keep the world with the cost-effective solutions for controller design. Basically, in hybrid cars, real-time simulation of self-designed controller using various distinct software and power hardware in the loop that would be reliable and cost-effective, having comparable results with real controller, because we were not having any kind of physical prototype in this project. Then comes the project hierarchy. And here it can be clearly seen that before defense, we did the thorough understanding of HIL setup and the basic literature work. Before the first evaluation, was successfully designed our boost converter and run it in open and closed loop. For closed loop, we designed the controller as well. Before second evaluation, we successfully designed our inverter and implemented it on HIL setup. And before internal evaluation, the design of a controller and controlling it with it to the PMSM motor was also achieved. And in the final step, we did writing of thesis and winded up our project. Now, this is plant model that we were going to use. It can be clearly seen that a boost converter is here, a DC link that provides stable voltages to the inverter, and this portion of the blocks is symbolizing or showing the PMSM machine. Then the design of boost converter. We designed the boost converter in MATLAB Simulink. It can be clearly seen the inductor, the IGBT, and the diode. Moreover, a capacitor and inductor can also be seen, which is used to minimize the THD, the signal losses. Then design of boost converter. For that, we did controller as well. We did design controller. And here it can be clearly seen that this portion of the code, the upper junk, is responsible for increasing the response, and RAM parameter is responsible for increasing the response. We have desired, we give it, and then comes the PI controller, and we feed V out process, P value of proportional, and pro value of integral gains, and this bitwise not, and the rest of the cases are responsible for changing the modes and every mode is responsible for a certain function, like zero mode for zero command, mode 1 for forced duty cycle, in which we set the duty cycle from to manual, and in mode 2 we do normal operation, and duty cycle is controlled by the PI, that is closed loop is done. And here we can clearly see this switches. These switches are also responsible for changing the modes, and we get duty cycle as output. So this was our controller that we designed for boost converter. Now let's move toward the lab view part of the same project, the same boost converter. It can be clearly seen that we are giving the reload reference, and it can be clearly seen the KP and KI again are set here, and we are getting duty cycle as an output along with the frequency here. Then our open loop results can be clearly seen that when we set our V out desired to 150, we change manually the duty cycle to get our V out process 142.73. It can be clearly seen that we are not giving P value of P and I as input, and mode 1 operation is done. So it is a kind of operation which in which we manually change the duty cycles. Then after running the boost converter in a closed loop, we got this response. V out desired is set to 200, and we set the value of KP and KI here 0.08 and 0.05 to get our desired output. In this case, the duty cycle is set by the PI controller to 50 in order to get our V out process to 201.15. Moreover, these perturbations can be seen. It represents the real world scenario that there are still a lot of perturbations in our signal that need to be mitigated. Here is the block diagram of our HIL setup. Basically, we deploy our closed loop PI controller in MyRio and our DC to DC boost converter in NIP-XIE. These two integrate with each other using the digital output and digital input pins. And then the digital output pin of the PWM generator is fed to the digital input of the NIP-XIE, and then it is fed to the EHS, electrical hardware solver, that then it is scaled down and converted to analog output, which is then fed back to the analog input and scaled up, then compared with reference and fed to the PI controller in order to generate the PWM signals. So for controller design, we did a comprehensive study, and after that we found that by comparing the sine wave and the carrier wave, we get PWM signals. Then for making or for designing the three-phase sine wave, we made this code in our lab view. And this whole chunk of code is responsible for generating three-phase sine waves. Then comes the carrier frequency generation, and for that, carrier frequency and modulation index are responsible, blocks are responsible, and they give us a triangular wave that can be clearly seen in the output block, in our output diagram. Then we generated the PWM signals using certain logics, and the output can be clearly seen in the diagram. Here is our inverter that we designed in MATLAB Simulink, 6 IGBTs along with the LCL filter can be clearly seen. And after running the whole setup, we got the output, our desired output that reaches 200. And these are the voltage signals of the inverter. And they are purely sinusoidal because we use the filter as well. Then we did certain tests. First was for frequency, and it can be clearly seen that when in current signals, when we change frequency from 100 to 1000 and from 1000 to 10,000 hertz, the signal get more and more sinusoidal with less and less THD. Then we performed a test with the voltage signals, and that was for modulation index. When we operated our system in under modulation with the modulation index of 0.2, we observed a dip, and then by running the system in over modulation, we got output signals of higher amplitude with greater perturbations. And when we set the modulation index to 1, we got clear signals, sinusoidal signals with appropriate output. Then we designed the inverter in MATLAB Simulink. For that, we made a certain block code for SPWM generation, and then three-phase inverter design was carried, and then the filter circuit along with the resistive load was connected, and the outputs were observed. The output of the output of SPWM generator was as follows, and the PWM signals that were generated were resembling the sinusoidal wave, like where the amplitude was high, the duty cycles were high over there, and where the amplitude was low, the duty cycles were low there. Then we clearly observed the output of our inverter without filter, and it can be clearly seen. Then by utilizing the filter, we got this clear sinusoidal waveforms. So here is a short video that can be clearly seen. Now I will run it. And when I run the program, now I will be changing the modulation index to observe the response. When over-modulated, the signals can be clearly seen that its amplitude has increased. Now in under-modulation, a clear dip is observed, but by keeping modulation index 1, we can clearly see the signals as uniform. And now we will be changing signals to current signals in order to observe the carrier frequency effect of carrier frequency. And when we decrease the frequency, we see these perturbations. And now when we set the frequency to the previous level, we see the observed signals. This was our inverter that we designed in MATLAB Simulink. And we can clearly see our lab part that was of carrier frequency generation, especially for SPWM generation signals. And it can be clearly seen. So it is the integrated plant model of our project. The whole process is the same, but here rectifier. The boost converter is replaced by a rectifier, and then the DC link is connected, and then inverter, and then the PMSM model. This was our B and F controller that we were basically designing. The DC link is coming from the DC link, especially. as an, it is fed here as an input. This ramp rate is responsible for setting the response faster, and the desired speed RPM is given as an input. We set the poles of the motor, and we get inverter frequency reference as output, the speed RPM set point as output, and modulation index is given as an input. And this whole chunk of code is responsible for giving a particular modulation index reference that would be responsible for running the system at a particular frequency, at a particular desired RPM. That would be responsible for running the system on desired RPM. Here is the output of our project, especially when we set the RPM to 3000 and the speed RPM set point and desired speed RPM were in phase with each other. The results of current signals can be clearly seen that three-phase sinusoidal signals were achieved, and these were the current signals in motor windings. Then when the speed was changed from 1500 RPM to 3000 RPM, a delay in the speed RPM set point was observed, showing the real-time delay, and it occurs in the real systems. Then here is another video of our project, that is final video, in which we can clearly see the outputs of the project. Now let's start the video. We set the supply voltage to 480. Now we are setting the speed set point to 1500 RPM with a ramp rate of 50. It can be clearly seen that the signal moves from 0 to 1500. Now ramp rate is increased, and it can be clearly seen that when the speed gets increased, the ramp rate would be faster. The response will be faster than before. PMSM phase currents can be clearly seen. The PMSM DQ currents and the DC link voltage of 800 can be clearly seen in this part of our project. This was the main output BI of our project. Now let's move toward the conclusion. Basically, starting from the first step, that was learning of HIL setup. Then we implemented our digital controller using LabVIEW and MATLAB both. Then we run our boost converter in open and closed loop successfully. Then implemented the three-phase inverter in HIL setup. Then we designed our controller for inverter in LabVIEW. Then the design of V and F controller, and controlling our PMSM with the same V and F controller was achieved. Here are the references that we took help from. This was the research paper, especially from Jahangir Badar, Somro, efficient hardware in the loop and digital control technique for power electronics teaching. And then from the second paper is from Daniel, and it was a permanent magnet synchronous motor control techniques, especially for motion control. And the third paper was again from Jahangir Badar's collections. It was efficient real-time controller design, test bench for power converter applications. And thank you. I conclude here. Thank you for watching. Follow us and share the video. Thank you.